In our two previous lectures, we talked about how we can write the equations imposed on the currents of a circuit and also imposed on the voltages of a circuit, imposed on by KCL and KVL, respectively, Kirchhoff's current law and Kirchhoff's voltage law. We said that that's the first step in order to be able to formulate a circuit so that we can solve for its currents and voltages. Okay. So today we will add a little bit more to our findings from the previous lectures, but before that, before we talk more about KCL and KVL or their formulations, let's briefly remember some of the basics that we saw in the two previous lectures. Okay. So here is our quick summary. So our aim was to write equations imposed on the currents by KCL, and likewise equations for voltages imposed by KVL. For that, since KCL and KVL only care about the interconnection of the components and not about the internal properties of the components, all we need to know when writing KCL and KVL is who is connected to who, component-wise. Okay? Since that's our goal, or that's what we need, a graph representation of a circuit is perfectly adequate for our purpose. So the first step was, or one of the first steps was, for a given circuit, obtaining its graph. Suppose that we're given a circuit and the corresponding graph is this. Okay. With 4 nodes and 6 branches. Okay. So, in order to be able to write systematically, we of course need the equations. We need proper labeling. Okay. So what we do is we label all the branches and all the nodes for KCL, writing KCL equations, and also we need to label the inner meshes when writing KVL equations. Okay. So this was our labeling from last time. Okay. This is branch 1, branch 2, branch 3, 4, 5, and 6. Okay. We not only give them labels, but also we assign each a direction. Okay. And then we label the nodes. This was our first node. This was our second node, third node. Okay. And then the remaining node, we don't require to label it. We assign that. We assign that node as a reference node. Okay. And then for writing the voltage equations for Kirchhoff's voltage law, we label the meshes, inner meshes. Okay. In this case, we have 1, 2, 3 inner meshes. So let's label them as mesh A. Note that a mesh must have a direction, and by convention, the direction we set is chosen clockwise. Okay, this is mesh A with clockwise direction. Let this be our mesh B with clockwise direction, and this guy here is our mesh C again with clockwise direction. And then when we write the equations KCL and KVL using nodes and meshes, some matrices appeared, okay? And those matrices were reduced incidence matrix, which appeared when we wrote the KCL equations, and the mesh matrix when we wrote the KVL equation, okay? And the reduced incidence matrix was such that for each node, excepting the ground node or the reference node, for each node that corresponds a row. And to each branch, okay, that corresponds a column. So since for this example we have 3 nodes, 3 non-reference nodes, that means our reduced incidence matrix must have 3 rows, and since we have 6 branches, it must have 6 columns. Okay. And how about entries? Entries were such that pick a row. Okay, to that row there corresponds a node. Okay, and then you look at that node and see what branches are touching to that node. For instance, for node 3 or for row 3, the branches that are touching to node 3 are 2, 3, and 5. And then you look at their directions. If the directions are outgoing from that node, the corresponding entry is +1. If it's incoming, the corresponding entry is -1. If the branch doesn't touch that particular node, then the corresponding entry is 0. Okay, for instance, let's do that node by node. For the first node, we have 1, 2, and 6. Okay, they are the branches that touch the first node. Therefore, the entries would be for those columns either be +1 or -1. So 1 and 2 they're outgoing, therefore it's +1. Okay, and then 3, 4, 5 they don't touch node 1, so the corresponding entries are 0, 0, 0. And finally, the branch 6 is a directional branch such that it's incoming to that node, node 1. So therefore, the corresponding entry in the row 1 will be -1. Okay. Similarly, for node 2, we have -1 because 1 is incoming, then 0 for 2 doesn't touch node 2, and -1 for 3, +1 for 4 because it's outgoing, and the remaining entries are 0. Okay, and then for the last row, we look at the last node, node 3. We have 0 for branch 1 because branch 1 doesn't touch node 3. 2 is incoming, 3 is outgoing, 4 is not touching, 5 is outgoing, +1, and finally 6 doesn't touch node 3. Therefore, that's the entries of our reduced incidence matrix. Okay, let me quickly check if I made a mistake. Okay, and then there is a similar construction for the mesh matrix. This time, again, we have the same number of columns, that is, for each branch there exists a column, and to each mesh there corresponds a row. Okay, we have 1, 2, 3 meshes, therefore the mesh matrix must have 3 rows. Okay, and the entries are such that, for instance, for the first mesh, which we labeled as mesh A, it has a direction clockwise, and then to that mesh there are 3 branches touching, okay, which are 1, 2, and 3. And then, so those, the corresponding entries will be either +1 or -1, and all the remaining entries will be 0 for that particular row. And then to determine whether it's +1 or -1, you check the directions. Okay, the direction of the mesh is clockwise, so as it goes along branch 1, the directions are opposite. This is going this way, branch 1 is going that way, therefore the corresponding entry is -1. Here it's same direction as branch 2, therefore the sign will be +1, and finally it's the same direction with branch 3, therefore the sign will be +1. Okay, so what we have is -1, 1, 1, and then the remaining branches doesn't touch that mesh, therefore the corresponding entry is 0. Then second row, second mesh, mesh B, we have 3, 4, 5, so 0, 0 for 1 and 2 because 1 and 2 doesn't touch mesh B, and then for 3, the direction is opposite, so that makes a -1. For mesh 4, the direction is opposite, so that makes a -1, and for branch 5, the directions are the same, so that makes a +1. Okay, and similarly for the last mesh, mesh C. Okay. Okay, and now these matrices appear when we try to write down KCL and KVL in terms of branch currents and branch voltages. And for compactness, we defined the following vectors. We stack all the branch currents in a single vector, and that vector we call the branch current vector. Okay? So this is a vector of size 6, and we have I1, I2, I3, I4, I5, and I6. Okay, that's our branch current vector. Likewise, we had branch voltage vector V1, V2, V4, V3, V4, V5, and V6. Okay, so those are the branch current, branch voltage vectors. Also, we defined node voltage vector. Okay, in this case we have E1, E2, and E3. We don't count the reference node, and that we call with E1, E2, E3. This is our node voltage vector, and node voltage vector simply means that sources E2 is the voltage that you would measure if you have a voltmeter and you connect the positive probe to node 2 and negative probe to the ground. Okay, so what you will measure is called E2, and so on. Finally, we have the mesh current vector, which we denote by IN. Okay, in this case, it's IA, IB, and IC. Okay. Now, when we write KCL and collect all the points coming from KCL, this is what we have. Okay, A times I equals 0. A being the reduced incidence matrix. I is our branch current vector. And then we discovered a peculiar relation between this matrix, or more probably its transpose, and the node voltage vector, and that relation was V equals A transpose E. And that allowed us to say that if you know node voltages, okay, which are in general much fewer than all the branch voltages, then you automatically can compute all the branch voltages. Okay. And then we had a similar set of equations when we try to express KVL. We express KVL in terms of writing KVL at each mesh, and that gave us n times V equals 0. So that's the KVL expression regarding that graph. And also, similar to this relation, we figured out the relation between mesh currents and branch currents through mesh matrix. What we had was I equals N transpose times I. Okay. So this is what we have discovered in the previous two lectures. Okay, and this is the first big step toward formulating a circuit. To those, we will add the terminal equations, and we will have what we need to figure out all the branch currents and voltages. Okay. Also, we saw a very important, arguably the most important theorem in network theory. It's Tellegen's theorem, which has a very short statement and also a very short proof. And the statement was this. That is, this vector, the current vector, and this voltage vector are always orthogonal to one another. Okay. So that's a mathematical fact, but it has a very important physical consequence, and it was conservation of power. Okay. So, given any circuit, the power at all times must be conserved, by which we mean the sum of magnitudes of powers delivered by certain components must equal the sum of magnitudes of powers that are absorbed by the remaining components. Now, there's one little disadvantage to this formulation, and that disadvantage is that in order to be able to talk about inner meshes, your graph or your circuit must be a planar circuit, okay, or a planar graph. But there are certainly circuits that are not planar, and in that case, this method is not directly applicable. Okay, so what we will do today is we will briefly, very briefly, not in detail is those constructions. We'll talk very briefly about methods, okay, that do not require the circuit to be planar for us to write down KVL and KVL equations. Okay. Okay, formulations for nonplanar circuits. Okay. Now, for this formulation, we have to introduce some new but very simple graph theoretical notions. Okay, the first of which is a tree. Okay, so what's a tree? Maybe some of you already heard about that. Given a connected graph, okay, let's say, well, for us it's describing a circuit. Let's give it a name that's called G, graph G. Its subgraph T is called a tree if the following conditions are met. First, T has all the nodes of G. Now that a graph in general is just a bunch of nodes, and some of which are connected by a so-called branch. Okay? Now this subgraph, if it is a tree, must have all the nodes of G, then it must be connected, and finally it must not contain any closed paths, which we call loops. T contains no loop. Okay? So it's a very visual definition also. So visual, that is clear why people have called it tree. Consider this graph. One, two, three, four. They are the nodes, and these are the branches. 1, 2, 3, 4, 5, 6. Now that we don't have to indicate the directions of the branches because this definition doesn't care about the directions. Okay, so that's our graph, which we labeled as G. Okay, graph G. Now this graph has many trees, some of which, for instance, is here. Okay, this is. Okay, first of all, it must contain all the nodes. 1, 2, 3, 4. All the nodes must be here, and it must contain some of the branches in such a way that the graph is, the subgraph is connected, and also it does not contain any loops. Now, clearly, this is a connected subgraph, and it contains no loops. Therefore, this is a tree. We can call it a tree. 3, T1. So what we have is 2, 4, and 5 as branches. Another tree would be 1, 2, 3, 4. Okay. And this would be also a tree. 3, 5, and 6 as the chosen branches. Okay? It contains all the nodes and it doesn't contain any loops. This is tree. T2, and also it's connected. Whereas this guy here, 1, 2, 3, 4. Okay. This is 1, 2, 3, 5. This is not a tree. Why? Well, it contains all the nodes. Therefore, the first condition is satisfied. It's connected. The second condition is also satisfied. But the third condition is not satisfied because it contains this tree. Well, it's not a tree. This subgraph contains a loop, and that's the loop 1, 2, 3. Okay, the closed path. So this is not a tree. Okay. Because it contains a closed path or a loop. Okay, so that's the simple definition of a tree. And note that this tree has 3 branches. This tree also has 3 branches. No matter what tree that you try to obtain for that graph, you will see that it always contains 3 branches, and that's not a coincidence. And the general observation, which is easy to prove, is such that for a connected graph with n nodes, the tree must necessarily contain always n-1 nodes. Okay, so that would be a nice exercise for those of you who are interested to prove. Okay, now we move on to the next definition, which is a little bit more subtle than the definition of a tree. Okay, but it's still simple enough. Our next definition is Cutset. Okay. Again, suppose that we're given a connected graph. We're calling it G. Let G be a connected graph. A set of branches of that graph, let's call that set C, okay, C for Cutset, is called a Cutset if 2 conditions are satisfied. Okay, if first removal of all the branches of C from the initial graph, the original graph G, makes an unconnected graph. Okay, condition 1, and condition 2 is if we remove all the branches of C except for an arbitrary one. And arbitrary one, the graph G, okay, stays connected. Well, in that case, it perhaps no longer is called graph G, but it's just a subgraph what remains from G stays connected. Okay. So let's see an example.
Suppose we have this funny looking graph. And we have a bunch of branches connecting these 5 nodes. Okay, and the branches are labeled as, let's say, 1, 2, 3, 4, 5, 6, and this last one is the 7th branch. Okay. Now, here we have a cut set C1, 4, 5, 7. Okay. So that set of branches, 4, 5, and 7, makes a cut set. Okay. And to show that cut set on the graph, we can make use of this dotted line. Okay. So that line or that curve crosses all those 3 branches, 4, 5, and 7, and that's claimed to be a cut set. Why is that a cut set? Because if you remove all those branches, what remains is, okay, so let me quickly draw it here, what remains is this and this node sitting on its own. Okay, because we removed 4, 5, and 7. This is what remains. So if you remove all the branches from the cut set, the remaining graph is unconnected. Clearly, it's an unconnected graph because there's no way that you can figure out a path from this node to the remaining nodes. Okay. But if you remove only 2 of them and leave out just an arbitrary one, then this node will be connected either by 4 or 5 or 7, depending on which one you left out, to the rest of the component, and the graph, in that case, the subgraph, will be connected. Therefore, this set 4, 5, 7 makes, according to our definition, makes a cut set. Okay. Now, clearly, there are many cut sets for a given circuit. Let's write down a few more examples. Another cut set is 1 and 3. Okay. This is C1. This is C2. Okay, it crosses 3 and 1. So that's also a cut set. It's easy to see why. Just apply the definition. And C3, another example is 6, 7. Okay. This is our C3. Okay. So these are all cut sets. And you can come up with easily more examples. Here's something that's not a cut set. Set 1, 3, 4, 5, 6. Okay? These 5 branches together, they do not make a cut set. Okay? This is not a cut set. And why is that? Okay, if you remove all of them, then what remains is here, this part, a node on its own, and then those 2 nodes connected together. Okay, so clearly the first condition is satisfied. The graph remains. The graph becomes disconnected if you remove all of them. But the second condition is not satisfied. Therefore, and I'll leave that to you to see that why that's not the case. The second condition is not satisfied. Therefore, this set is not a cut set. Okay. Now, having defined having defined cut set and a tree, now we're going to combine those 2 definitions to introduce a new further definition, which eventually will allow us to write KCL in a systematic fashion. And that's the thing that we're going to call is fundamental Cutset. Here is a fact. Given a connected graph, G and a tree T, that's a tree of the given graph G. Okay. Let beta be a branch of T. Well, automatically it's also a branch of G because T is a subgraph of T. Then there exists a Cutset of G that contains beta, okay, the given branch of the tree, and no other branches from T. Okay. Now it turns out that when you try to figure out a Cutset that satisfies that constraint, you can always find one Cutset, and more interestingly, that Cutset you can find is unique. You cannot find another one that satisfies that constraint. Because of that uniqueness, we're going to call that particular Cutset a fundamental Cutset. Okay. That Cutset is unique. Okay. We're not proving this, we're just giving it as a fact. It's not that obvious. That Cutset is unique and it's called fundamental Cutset. Okay. Okay, so here is an example. Suppose that this is our graph with 9 branches and 6 nodes. Okay, 6 nodes, 9 branches. And here are the branches. 1, 2, 3, 4, 5, 6, 7, and 8, and 9 branches with their directions. Okay. Now, for this, let's choose a tree, or suppose that that tree is given. So, this is the tree. I'm gonna make the tree branches a little bit darker so that we're gonna see what is tree and what's not tree. So, branch number 1 is part of our tree. 3 is one of our tree branches, and we have 5 in our tree. And 8 and 9. Okay, the darker branches, they belong to tree. So this is a tree because all the nodes are touched, contained, and it's connected and contains no loops. Okay, tree branches. Okay, 1, 3, 5, 8. And 9. And then the remaining branches we call Cotree branches. Okay, so Cotree branches are
what remains from the branch set of the original graph once you remove the tree branches from it. Okay? So Cotree simply means non-tree. Okay. Okay. So what remains is 2, 4, 6, and 7. Okay. Now, let's go tree branch by tree branch and try to figure out the so-called fundamental cutset for each tree branch. Okay? So let's start from branch number 1. Here is our branch, and there are many cutsets that contains that branch. Okay? For instance, this would be a cutset 1, 3, 6, 9. This would be a cutset 1, 3, 5, 4, and so on. Okay? But those two cutsets are not a fundamental cutset, because in order for a cutset to be a fundamental cutset, it should contain only a single tree branch. All the other branches must be coming from the Cotree. Okay, under that constraint, it's easy to see that the fundamental cutset associated to the tree branch number 1 is this. Okay, that is the cutset that contains branch 1 and branch 2. Branch 2 is coming from the Cotree, branch 1 is coming from the tree, therefore that constraint is satisfied. Okay, and that's a fundamental cutset. If you remove those two, what remains is this part of the graph and this node sitting on its own. Okay, and then move to third branch, tree branch. Okay, now this is the cutset or the fundamental cutset associated to that branch. So let's call this C1. Let's call this C3. Okay. There's only one tree branch. All the remaining branches coming from the Cotree. And then let's move on to the next one, branch number 5, and it's this here. Okay. This is C5 that contains 4, 5, 6, and 7. And move on to next tree branch, branch 8. It's this C8 that contains 8 and 4. And finally, cutset 4, branch 9 contains branch 9 and branch 7. So this is C9. So those are all the fundamental cutsets for the given tree. For a different given tree, then the fundamental cutset will naturally be different. Okay. Now, up to this point, we haven't talked about anything related to circuits. Okay. All we talked about was from graph theory, but now, using the cutsets, we will be able to introduce KCL into the picture. And it's as follows. At each cutset, we can obtain current equations imposed on the circuit by Kirchhoff's current law, by KCL. That is, for each closed surface, sum of incoming currents must equal the sum of outgoing currents. And now, those cutsets we will use to construct our so-called closed surfaces. Okay? For C1, you can consider this as a closed surface, therefore incoming current I1 must equal outgoing current I2. So this cutset gives us the equation I1 equals I2. This cutset, for instance C3, we can consider this as a closed surface. I2 must equal I3 plus I6 plus I7 and so on. Okay. So let's go cutset by cutset and write the equations. Okay. I1 equals I2, but let's write it following the convention that the current that belongs to the tree, which makes that the tree branch, which makes that particular cutset, let's consider that as our reference direction of that current. So the reference direction is okay, let's say incoming, then we consider all the currents as incoming, and sum of all those currents must equal to 0. So I1 is incoming, and minus I2 is incoming, and that's all that equals 0. C3, okay, this is the tree branch that's associated to that particle Cutset. Let's say it's outgoing, so we're going to consider all the currents as outgoing. So I3 is outgoing, I6 is outgoing, I7 is outgoing, and minus I2 is outgoing. So we have I3 minus I2 plus I6 plus I7 equals 0. Okay, and C5, okay, let me quickly write down the remaining ones. I5 plus I4 plus I6 plus I7 equals 0. C8, I8 minus I4 equals 0. And finally, for the last Cutset, we have I9. That's our reference direction. Okay, suppose it's incoming, that's incoming. I7 is also incoming. I9 plus I7 equals 0. I7 equals 0. And that's the set of equations imposed on the circuit by KCL. Okay. Now, we're going to do something similar for KVL, but before that, let me put down this remark. And note that once all the Cotree branch currents are known, the remaining currents, which are necessarily tree branch currents, the remaining branch currents can be computed. Because here the first currents are always, because we wrote it that way, they are the currents coming from the tree branches, okay? And then all the remaining currents coming from the Cotree branches. So that means if you know this part, you can easily compute the tree branch currents. Now let's also very shortly talk about what can be said about KVL, okay, in this new way of looking at things. And for that, we have to introduce one last notion from graph theory, and that's called fundamental loop. Since we're using the word fundamental once again, there's some uniqueness in our definition, okay? And it's as follows. First, remember what we saw about fundamental Cutsets. Remember that each tree branch defines a unique Cutset, okay? Since it was unique, we called it a fundamental Cutset, Okay. Likewise, each Cotree
branch defines a fundamental loop, fundamental closed path, in the sense that that loop is constructed from that particular Cotree branch, and all the remaining branches are coming from the tree branches. Likewise, each Cotree or non-tree branch defines a unique loop. Okay, and because of this uniqueness, we're gonna be calling them fundamental loops. Called fundamental loop, such that it contains only one Cotree branch. So cutsets, we treat them as closed surfaces or use them to construct closed surfaces, and then once you have a closed surface, you can apply KCL, and that will give you certain relations, certain constraints regarding the currents. And whenever you have a loop, a closed path, you can directly apply KVL to the voltages involved, and we're going to do this, we're going to do that on fundamental loops, and that will give us enough many equations from KVL on the voltage. Okay. But first, let's be clear about how we construct fundamental loops. Okay. Let's stick to the same graph as before. Our 6-node, 9-branch graph. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And let's work with the tree that we have picked in the previous example. So let me darken the branches that belong to the tree. Okay. And finally, branches 8 and 9. Okay, so that's our tree. And what remains, or the remaining branches, are Cotree branches. So, Cotree or Cotree branches are branch numbers 2, 4, 6, and 7. Now here, it was claimed that each of those branches, 2, 4, 6, and 7, they can be used to define the loop closed path in such a way that that loop contains only one Cotree branch, and all the remaining branches in that loop are coming from the 3 branches, namely branches 1, 3, 5, 8, and 9. Okay, and also the part of the claim is that that loop must always be unique for a given Cotree branch. Okay, so let's see whether that's true, at least for this example. So here we have a Cotree branch, and this Cotree branch defines the following fundamental loop: 2, 3, and 1. So they make a loop, and it's a and that loop is such that only 2 is a Cotree branch, 1 and 3 are tree branches. Therefore, it must be a fundamental loop. Okay. So this is a fundamental loop defined by the Cotree branch 2. And let's assign a direction to that loop, because we will need that when we write KVL. And that direction, by convention, same as the direction of the
Cotree branch. That's defining that fundamental loop. So that's the direction of the Cotree branch. Hence, direction is clockwise for that loop. Then we have 4, Cotree branch 4, and that should define a loop. That should define a loop, fundamental loop. And that fundamental loop, not surprisingly, is 4, 5, and 8. It's easy to see. And its direction is, again by convention, same as direction of the branch, which is in that direction. Therefore, it makes the direction of the loop counterclockwise. Okay. And we have 6. Okay. And the loop that's determined by 6 is 3, 6, and 5. The direction is clockwise, same as the direction of the Cotree branch. And finally, we have 7. Okay, incidentally, all those loops, loop 4, 2, 6, and 4, they were also inner meshes, but it's not the case for the last fundamental loop. That is the fundamental loop determined by 7. Note that you can consider this as a loop, 7, 9, and 6, but that's not a fundamental loop because it contains 2 Cotree branches. Okay, but the constraint is such that it must contain only a 1 Cotree branch. All the remaining branches must come from tree. If you apply that constraint, then you see that this must be your loop 7, 9, 5, and 3. Okay, because 3, 5, and 9, they are 3 branches, and the direction of this loop must be same as the direction of the Cotree branch 7. Okay. So branch 2 defines loop 2. Okay. That is 2, 3, 1. And branch 7 defines loop 7. That is 7, 9, 5, and 3. 7, 3, 5, 9. And the remaining loops we already talked about. Okay. And now finally, since we have loops, we can now apply KVL to obtain the voltage equivalence that we require at some point if you want to solve a circuit whose graph is that. Okay, at each fundamental loop, we can obtain voltage equations by Kirchhoff's voltage law. Okay, now that this sentence looks very similar to a sentence that we constructed just very recently, where at each fundamental Cutset we wrote current equations imposed on the circuit by KCL. Okay, so we have 4 fundamental loops, so that makes 4 equations, 4 voltage equations. Okay, 2 for loop 4, for loop 6, for loop 7. Okay, for loop 2, we write V2 plus V3 plus V1 equals 0. Okay. Okay, V2 plus V3 plus V1 equals 0. Sum of all those voltages, and they're in the same direction with the loop, therefore all the signs are positive, equals 0. For the loop 4, we have V4 plus V8 minus
V5 because the direction of V5 is opposite to the loop equals 0. So we have V4 plus V8 minus V5 equals 0, and for loop 6 minus V5 minus V3 equals 0, and finally for loop 7, V7 minus V9, because the directions are opposing to one, and minus V5 minus V3 equals 0. Minus V9 minus V5 minus V3 equals 0. Okay. And let's end the lecture with this remark. Note that once all the 3 branch voltages are known, the remaining branch voltages, namely the Cotree branch voltages, can easily be computed. The remaining branch voltages can be easily computed. The reason is as follows. Note that the first voltages in our equations are the voltages corresponding to Cotree branches, and all the remaining voltages, they are the voltages associated to Cotree branches. So that means if you know the Cotree branch voltages, then all the remaining voltages, or if you know the 3 branch voltages, then you can easily compute the Cotree branch voltages.